We got into this field because we couldn't make fiberglass blades properly. We will talk more about that later. Wooden blades is quite easy to make, at least in Nepal. Can we pass a few around? Just, and then we can pass some bigger ones around as well. Can you catch Leon? Oh, yes. That one with the crack in has been tested for strength and has reached its limit. The other one hasn't been tested as yet. What we find is the skills in Nepal are, of course, very much related to hand skills. And we had noticed that there are many wooden idol makers in Kathmandu who can copy by eye a quite intricate design, and we thought we would try to see whether the carpenters could copy a wooden wind turbine blade, and we found that they could. But the question is, if you're going to make a blade out of wood, well, you start with your tree. You cut down a tree. Typically, we have no control as to which tree is cut down. Say, this one. There it is, 12 tons of wood. And which bit do we take for the blade? What do we expect? Normally, you use a radial saw, radial cut, because it reduces the amount of shrinkage and gives you generally a more consistent piece of wood. But if we take a piece of lakuri tree, whoops, and just cut it like this, turn it upside down, and then measure the elasticity of these different pieces, it varies hugely. Now, the black ones are for wet wood. The red is for dry. And we see that it's not a very consistent process. So we look here, it has elasticity of some 47, this one is 67, and this one is 10. And I saw this result and I wondered, were they wrong? Badly wrong. So I asked to see the samples, and you could flex them by hand and you can feel the difference. The difference is massive between one adjacent piece and another. So this is challenging. What is going on? If the screen was straighter, the blades would look straighter as well. They're not really undulating like that. So we had 4 blades made, just from dried pieces of timber. You see that they have different colors, different grain directions. We see how we go. If we plot the Young's modulus in a sort of 3-dimensional process, we see that mostly the stiffest bits are up here. This bit, there's a little bit of stiffness there, touch there. When we look at it again, whoops, sorry, why would it be concentrated in certain areas? We look at the density. Well, the density doesn't correspond very well with the stiffness. You think it might do. A little bit of high density down here, this tends to be on the lower density side. So somehow those pieces of wood are different. There are some 4 types of main pieces of wood inside the tree that I can find anyway. The pith, the juvenile wood, normal wood, and reaction wood, which is either compression or tension. And what we're doing with these woods, the tree is trying to stay straight. Right? If the trunk is bending, then either a tension wood grows on the upper side to pull it straight, or a compression wood grows on the underside to push it straight. The fact that branches go like this is because of the reaction wood in them. Some trees have sagging branches, weeping branches we call them, and they are devoid largely of the reaction woods. Where are those? The pith is at the center of the trunk. The juvenile wood is near the center, around the pith. The normal wood, providing the tree trunk has been straight from birth, so to speak, it is in the straight section. But the reaction wood forms to keep the tree trunk straight. And you get this wood even if it has corrected, because it's still required to keep it straight. As an approximation, the juvenile wood, which is near the center, is going to have less density, less strength, less stiffness, and shrink a lot less. So if your blade consists in part of juvenile wood and it hasn't fully dried, it's likely to crack. This is in the southern pine, it's a cross section, and it has been marked, this section has been marked as compression wood. You get wide, dark rings. It's also an elliptically set trunk, which apparently is characteristics of trunks with compression wood. This is on the underside of the linden trunk. These tend to be the pines, the softer woods. So we're going back to here. We see this is certainly not a round piece of trunk. Almost certainly it has some reaction wood. It's going to, being a hard wood or an angiosperm tree, we're going to have, in this section, which I believe is probably a tension wood, this is the uphill side. I hope I've got that one right. So it has been leaning like this, down the hill a bit, so this side is pulling the tree straight. We can expect it is under tension, and if you cut a piece of wood that is under tension, it's going to shrink. And apparently even a 2-degree lean is sufficient to cause tension wood. I have read you can identify it by a gelatinous layer, but it seems that you need to do that microscopically. Now we just get rid of this non-genuine window. Sorry?
Just click on the slide.
Okay. So we're back to our blades again. What we're seeing here is discoloration. It looks like knots. We're seeing movement of the grain, different grain widths here from here. I suspect this particular blade will not give the same performance as, say, this one here, which is beautifully straight grain all the way across the same angle. Grain slope is also a factor. We have only just started to investigate this. So, for example, we have a grain slope of 1 in 20 here, 1 in 23 here, and you square them, sum them, and take the square root to get the overall grain slope. 2 pieces of wood, which is identified as about a 0 grain slope here, and about a 1 in 4 here. And from, this was scaffold boards, but European whitewood. So as the slope of the grain increases, the rupture strength tends to decrease. Okay? But even still, for the same set of timbers, we're getting quite a large variation. And that makes it challenging when working with wood as a high-precision structural element. You can model this, and people have done this. This is modeling Sitka spruce, which is one of the, probably the preferred timber for wooden aeroplane blades. The small blade, the small aeroplanes like microlights tend to still use wooden blades. And I'm just going to illustrate the number of variables that have been involved in modeling the timber to try and predict its performance. So we had the tree variables, the log variables. Now we have the piece of wood variables. Then we have the edge variables on the wood. Then we have the knot distribution variables. And with all of those variables, we end up being able to model a line here, which is nicely centered around the experimental points, but there's quite a decent scatter there. So even with something like 10 variables, at least 10, we're still looking at a 40% plus or minus type error rating. The other issue appears to be where you take the timber from. And you can see that the lower parts of the tree tend to have a different shape from upper. So the height above ground forms the basis of declaring a butt log near the butt of the tree or an upper log higher up. So in Nepal, we have these range of trees. These are 6 of the 8 that we have tested. The preferred one we have as wind turbine blades is this Lakuri, because it's resilient, it's reasonably light, and it's reasonably available. So when we do static testing, you pull it with a force, we measure its change in position, we get some different curves until they snap. So is there a pointer somewhere here? Not today. Maybe I can use the wind turbine blade. Thank you. So here, for this particular tunny samples, it stretches, goes a little bit plastic, and then just breaks. For the Lakuri, it gets to an elastic point, and then becomes plastic for quite some time, or distance before it snaps. Some, like this saw, become incredibly plastic and accelerate in their lengthening, as you can see from the stress strain curve diving. It's interesting to contemplate, can we use this plastic region as a warning? So in other words, we're operating in the elastic region here, but should we get to this region for some reason or other, it's going to throw the turbine out of balance. If we can measure the imbalance, the vibration, we know that something's going wrong and shut it down quickly. But what does it really mean, all these figures? Here is the blade attached to a stand which is attached to the wall, and it's being bent. This is Lakuri wood. This, I think, would go to 90 kilos or so. At this point, it's 2/3 the way from the hub, more or less some sort of midpoint where the forces will go. You can see it's very, very linear, beautifully linear, until we get, which way around, until we get somewhere in the order of 600 Newton meters, but the actual braking doesn't occur till over 900 Newton meters.